In 1935, a man by the name of Edward Schrödinger published a thought experiment that would break people's brains to this day. Schrödinger contended that if you took a cat, put it in a box, took a hammer and connected it to a glass cube filled to the rim with poisonous gas using a radioactive isotope, at some point the isotope would decay, the hammer would swing, the glass would break, and the cat would die. Given the spontaneous nature of radioactive decay, if one sealed this box, one could not know whether or not the cat was alive or dead. Schrödinger's conclusion was that while in the box, the cat took a state of both alive and dead. Only when one opened the box could one force the universe to choose an outcome. While Schrödinger published his thought experiment to demonstrate what he viewed as the absurdities of the quantum paradox, he inadvertently created a very easy way to conceptualize a very hard thing to understand. One of the core tenets of quantum mechanics, wave-particle duality. Hi, my name is Hudson Milano, and this is just one of the many fascinating mysteries that quantum mechanics has to offer. Now, I'd like to be clear. I'm not a genius, and this speech isn't going to make you a genius. Because these topics are so complex, we're only going to scratch the surface here. Anyway, let's get into it. The first topic that we're going to be talking about is probably the hardest to conceptualize. It's the aforementioned wave-particle duality. And since it is such a ridiculous mess of esoteric wizardry, I'm going to do a semi-live demonstration for y'all. So, strap on your physicist caps. Imagine we are doing an experiment where we're shooting an electron through one of two slits and registering it at the back. What do you expect to happen? If you're thinking in Newtonian terms, then when I shoot the electron, it'll go through a slit and will register at the back. Simple, right? Well, the data actually looks a little bit more like this. Each dot, by the way, represents a single electron that we fired. Now, what could have happened here? This obviously doesn't make any sense. The data, while it should be acting like, well, a particle, seems to act more like a wave. I mean, look if I shoot a wave through the same two slits. Similar shape, right? Let's try something different. This time, let's shoot the electron through the same two slits, but let's measure which slit it goes through. All right, here's the data. Well, this doesn't make any sense. This is clearly different data from before. I mean, it does make more sense than the previous data. This is what we would expect from this situation. We shoot the electron and it hits the back. But what is going on? It seems that when we measure the particle, it acts like a particle, but when we don't measure it, it acts like a wave. This was the experiment that was done from 1923 to 1927 by Lester Germer and Clinton Davidson. Alrighty, just to make sure what we're seeing here is true, let's do one more experiment. This time, we're going to shoot the electron, and it's going to hit a crystal. This crystal will split it into two quantumly entangled particles, something that we'll get to later. Anyways, when we shoot the electron, the first quantumly entangled particle will do the normal double slit experiment. The second quantumly entangled particle will do some pinball-like action until it hits either a beam splitter or a detector. If it hits a detector, then we will know the path the other particle took, given the quantumly entangled nature of the particles. If it hits a beam splitter, then we won't. It is very important to note that the second particle will move much slower than the first one. The first one will have already hit the detector by the time the second particle has hit its destination, but we will not know the data until the second particle has hit its destination. Alrighty, here's the data when the particle hits a detector, and here's the data when the particle hits a beam splitter. This doesn't make any sense. What seems to be happening is that the first particle is going back in time and changing whether or not it is a wave or a particle based on whether or not we know which slit it went through. Alright, if your brain just broke, mine did too when I first read that. But luckily that's not exactly what's happening. Something equally insane is going on. I'll let you in on the secret. One of the core tenets of quantum mechanics is that when a quantum particle can act as both a particle and a wave at once. This is an example of what is called a superposition. When the wave itself is called a wave function. This is because we can do a mathematical formula to see roughly where the particle will be. If you're confused, just remember this. When we don't measure what the particle is, it acts like a wave. When we do measure where the particle is, the wave function collapses into a single distinct particle. Alrighty. Congratulations, you guys know about 90% more about quantum mechanics than most people out there. But we're not done yet. No, we've only just begun confusing ourselves. The next big thing that we're going to talk about is quantum entanglement. Quantumly entangled particles are basically inseparable. Whenever one does something, so will the other. They must be created by the same occurrence. An example being the crystal that we used in our experiment too. Whenever a scientist measures a quantum particle, they will know that the other one is the same way. As you might imagine, this can be very, very useful. Unfortunately, the quantumly entangled state is actually very, very fragile. If even a single particle touches another quantumly entangled particle, both quantumly entangled particles will revert back to their normal state. Alrighty, final big tenet before we get to talk about some of the cool things that we can do with this. And it is called interference patterns. Interference patterns is not actually a part of quantum physics. It's a part of regular physics, but I figured it'd be something interesting that we can talk about because it'll make stuff easier to stomach later. Basically, it's simpler than you think and only has two big rules. The first rule is that two waves can exist in the same place at once. The second rule is that depending on how those waves line up, they will either amplify each other or cancel each other out. Alrighty, we did it. We got through the boring part of the speech. Now we get to talk about some of the cool things that we can do with these quantum mechanics. And if you thought that the tenets of quantum mechanics were magical, well, what you're about to see is pure fantasy. Alrighty, first, what do you think of when you think of things that go faster than light? You might think of certain ships from pop culture that we won't name because we don't get a copyright struck. But there is one thing that all of these ships have in common. They don't mention how they get past the proverbial intergalactic speed limit. As far as we know, nothing can go faster than the speed of light. However, there are some workarounds in quantum mechanics. This is actually why Einstein hated quantum mechanics, calling quantum entanglement specifically spooky action at a distance. Any of these theorized substances, and anything else that doesn't fit into the rigid box of physics is called exotic matter, and a few examples of it are dark matter and superfluids. The specific type of exotic matter that we need for our warp drive, however, is matter with negative mass. If we take this matter and we put it in an engine, we can create what is known as the Alcubierre warp drive. This leads to what might be my favorite quote in all of science. Alcubierre describes the effect of this as a modification in space-time. Essentially, what you're doing is you are contracting space in front of you and expanding it behind you. This causes a sort of bubble of space-time around you. Inside the bubble, nothing abnormal is happening. In Newtonian terms, you're not even moving at all. Everything else is just moving around you. However, outside the bubble, this motion breaks the speed of light. There is a catch. It might require more energy than all of the universe combined. However, with recent revisions, this number has actually been slimmed down a lot. While the Alcubierre warp drive may still be science fiction as of now, something that isn't science fiction is quantum computing. Quantum computing is based on the interference patterns that we talked about earlier. Remember your two rules. First things first when it comes to quantum computing, we cool the room down to sub-zero temperatures. This will make more sense in a little bit. Second things second in quantum computing, we get a lot of qubits and we quantum entangle all of them. Qubits don't work like normal computer processors. Whenever a normal computer processor can only be a 0 or a 1, whereas a qubit can act as both, because the electrons housed in it are in a superposition, they can act as both at once. The reason why we actually cooled the room down to sub-zero temperatures is because we can't let a single particle touch this quantum entangled state. Remember, if a single particle touches it, the whole thing collapses. All right, now the interesting part begins. The quantum computer, given that all the electrons housed in it are wave functions, will begin to exhibit interference. Correct answers will amplify each other, where negative answers will cancel each other out. So when it's measured, only a single correct, distinct answer will remain. Sounds complicated? Well, it is. Luckily for us, I found a pretty good analogy for it. Imagine you have a very complicated maze. A regular computer will run down into every single dead end and turn around. A quantum computer works more like this. Imagine a mist going through the maze and going through every single possibility at once and reaching the correct answer much faster. Quantum computers aren't exactly practical yet. It takes a lot of energy to keep the room in a sub-zero temperature, and it's very, very unreliable to keep qubits in an entangled state. However, it can be used for modeling complex systems, such as the effects of medicine on a cell, financial markets, or even improving cryptography. All of these things are limited by the number of variables that a computer can contain. What I really hope that you take away from this is that science and technology are so much more interesting than we think. And when you begin to scratch the surface, the impossible becomes possible. Thank you.